Diffraction and interference of light. Diffraction. When sound waves and water waves meet an obstacle, they bend around it. This phenomenon is called diffraction and explains why you can hear a person around a corner even though you can't see her. When waves meet a small opening, such as in this barrier, the opening generates a new wave on the other side, which we can see propagating over here from right to left. Let's look at diffraction in a little bit more graphic detail, a little easier to see. When waves meet an obstacle, they bend around it. The waves meet a small opening. The opening generates a new wave on the other side. Here we have three diagrams. In the first case, we have a partial barrier here on the left, and we can see that the wavefront generally remains straight as it is here at the bottom part, but we have a curved wave that is generated off the top and moving to the right. In the second case, we have a gap in this wall, and again we can see that there's a new wave generated. Again, you can see the curvature at the top and at the bottom moving to the right, and a fairly flat wavefront. In the third case, we're shrinking the gap in the wall, and what we see here is a new wavefront that is mostly curved. The second phenomenon we're going to look at is interference. It was also observed that light bends around objects, and when it meets the light from the other side, it creates a bright spot where it would be least expected. Here's a picture of the shadow from a coin. The light that is shown on a coin creates a shadow behind it. But in certain cases, depending on the light wavelength and the coin size, a bright spot would appear in the middle of the shadow. The diffracted light from one part of the disk interferes with the diffracted light from the other part and produces a bright spot in the middle. Let's put the two phenomena of diffraction and interference together. What if we have two or more wave sources bending around an obstacle and then running into each other? Well, what we're going to get is a much more complex pattern than we've seen, much like the picture of the water waves that you see here on the left. In 1801, Thomas Young conducted a very famous experiment, a very critical one. He wanted to see if light would behave like water waves, forming ripples after it passed through two openings. This was known and is known as the double slit experiment. In the case of water waves, the interference effect becomes more pronounced as the wavelength of the water wave approaches the width of the opening. Since the wavelength of light is much less than that of water waves, the openings would have to be very, very small to see any effect for light. But first, let's assume that light acts like a particle and predict what would happen if a beam of light particles strikes a wall with two holes in it. All right, so let's consider light as particles, or in this case, baseballs. And so let's have Cy Young cloned and have the two Cy Youngs throw a large number of baseballs through openings in a wall just a little bit bigger than the size of the ball. The top baseballs would hit the red target, and the ones thrown by the bottom Cy Young would hit the blue target. If light was just a large number of particles, one could expect a similar pattern on the back wall, two bright spots, each spot directly across from the opening. Here's a picture of Young's double slit experiment, a simulation if you like. He conducted his experiment by passing a single color of light through two slits. The result was he didn't see two bright lines on the screen opposite. Instead, he saw a pattern consisting of alternating bright and dark lines or fringes which decreased in intensity from a peak in the middle. And if you look at this, we're seeing a bright spot here in the center, which is between the two slits, and then additional ones above and below. Let's look at this in more detail. Here's Young's sketch of his results. If you look over here, points A and B represent the sources of light, and points C, D, E, and F show various stages of interference. Here we see a diagram of Young's double slit experiment again. The monochromatic light source here on the left, a wall or screen with two slits in it to allow the light to pass, and a measurement screen here on the far right. What you'll notice is that the light hits the two slits, generates two diffracted waves, and at the far end we see a complex pattern which is very reminiscent of sound or water waves. And as a consequence, Tom Young concluded that light, like sound and water, travels as a wave. Let's try to understand why we see maxima and minima, these bright and dark spots. Interference occurs because each point on the screen is not the same distance from both slits. So depending on the path length difference, the wave can interfere constructively with a bright line or bright spot, or destructively with a dark spot. If we look at the three diagrams below, we can get some initial understanding, qualitative understanding. In the first case, on the left, we have two waves going through two slits and traveling exactly the same distance to the screen. Consequently, the number of wavelengths that it will take for each wave to get from the slits to the screen is identical. They will be in phase, they will constructively interfere, and we'll get a bright spot. In the second case, in the middle, we have the two waves traveling at an angle theta with respect to the normal to the screens. And in this case, one of the waves travels one full wavelength further than the other. But because it's one full wavelength, the two waves are still in phase at the screen, so they interfere constructively with the result of another bright spot. In the last case, here on the right, the difference between the paths is a half a wavelength. Consequently, the two are out of phase and destructively interfere, yielding a dark spot on the screen. To summarize the discussion on the last slide, and to compare with previous work that we've done, we know from the wave chapter that waves will constructively interfere at a point when they are in phase, that is, their peaks coincide. This occurs when the distance of two waves travel differs by an integer number of wavelengths. And for light, this constructive interference results in a bright fringe. Dark fringes occur where the waves destructively interfere, that is, when the waves are 180 degrees out of phase, or a half a wavelength difference in distance traveled. These occur between bright fringes. Let's try to understand geometrically where double slit maxima and minima come from. The bright lines that appear on the screen are called maxima. The dark lines are called minima. Maxima are evenly spaced, and a minimum occurs between each pair of maxima. The distance to the first maxima can be found by using a method of similar triangles. This should be familiar from the waves and sound units, but just to remind you, the difference in the distance traveled for an angle theta is going to be given here. D sine theta, the opposite to the angle theta with the hypotenuse equal to the distance between the slits. That distance has to be an integer number of wavelengths if we're going to get constructive interference. So just to summarize what I think we know from the past, d sine theta equals m lambda, where m is an integer. So as we discussed in the last slide, a constructive interference pattern will occur when d sine theta is equal to m lambda. That is, the path length difference of one wave relative to the other is an integer number of wavelengths. It then makes sense, of course, that a destructive interference pattern will be given by d sine theta equals m plus a half lambda, because that means that the two waves will be out of phase by 180 degrees and destructively interfere, leaving a dark spot or a minima. M is called the order of the interference fringe. In the case of light, the distance between the successive maxima, which we're going to call x, is very small relative to the distance between the slits and the screen, which we'll call L. So because we have small angles less than 10 degrees, we can approximate that the sine of theta is the same as the tangent of theta. Since the tangent is x over L, we can use sine theta equals x over L for these small angles, and our d sine theta equals m lambda for maxima becomes dx over L equals m lambda. So let's use this and extend it to the minima as well. So we have two equations. The distance between successive maxima, or the distance from the center to a maximum, is given by x is approximately equal to m times lambda times L divided by d. Again, where m is the order of the interference fringe, lambda is the wavelength, L is the distance between the double slit and the screen, and d is the distance between the two slits. For destructive interference, we have exactly the same equation, but we add a half wavelength. So we have the distance between from the center to a dark fringe is given by x equals m plus a half lambda times L divided by d. The maxima and minima spread out as the distance between the slits gets smaller, and d gets, so what we're basically saying is that as d gets smaller, the distance between the slits gets smaller. I repeat, the distance between successive maxima or minima increases. Here's a picture of the maxima and minima profile, if you like, the fringe profile on a screen. What you see here is along the y-axis, the brightness, and along the x-axis, the distance, which we just denote by the orders of the fringes. As you can see, as we move away from the center, whether to the right or to the left, the maxima diminish in brightness. Now, when Young did his double slit experiment, it was done with monochromatic light. An interesting question is, what would happen if instead of monochromatic light, we used white light? Well, as it turns out, with white light, all of the waves are going to be in phase at the central maximum, so they will constructively interfere. As we move away from that, each of the maxima are going to depend on the wavelength. Consequently, for different colors of light, the position of the maximum relative to the center is going to be shifted. And we get a rainbow effect, as you see in this diagram. Here's a summary of what we know from the double slit experiment. It relies on two properties of waves, diffraction and interference. These together enabled Young to claim that light is a wave. Each slit generates a new wave due to diffraction, and those waves either constructively or destructively interfere at the screen, which is at a distance much greater than the distance between the slits.